Welcome back to 10-Minute Science. Last time, our network guessed cat, and cross-entropy graded it with a single number, the loss. That number, predicted minus true, tells us how each score tilts the loss. Now watch the orange pulse flow backward. That is today's topic. The network can only change its weights. Watch the wave. Every line that lights up is a weight. Learning means moving each one so the loss goes down like the ball in the panel. And for that, every weight needs its derivative. Today, backpropagation, all of them, in one backward pass. Let's build the full picture. The photo becomes the vector x, follow the signal. W1 turns x into the sum c, and ReLU bends those into the hidden layer h. Each value the forward pass computes glows gold. It is saved, because the backward pass will need it. W2 turns h into 3 scores. Softmax makes them probabilities, and cross-entropy grades them into one number. The loss in the gold box. That left-to-right run is the forward pass, and every value it touched is now saved in gold. Each box is a value. Each arrow is one simple operation. Together, they form the computational graph. And backpropagation is a walk across this graph, right to left. Look at the loss box. For house prices, we use squared error. For classification, cross-entropy. Different formulas, one job, measure how wrong we are in a single number. Training means making it smaller. To find one weight's direction, hold the other still. This curve is the loss against that single weight. Push the weight a little, the green step, and the loss answers with the orange rise. Their ratio is the derivative, that curly D symbol. A positive derivative means raising the weight raises the loss. This is why we subtract the derivative. The gold tangent is the derivative, positive here, so the weight must move left. Watch the ball cross over. The derivative turns negative, so it moves right. Either way, downhill. And ETA, the learning rate, scales that raw derivative down to the small green step. Now count the weights. Thousands here, millions in a real network. Gradient descent needs every derivative, fresh, at each step. Together they form the gradient. Getting 1,000,000 of them is the real problem. The direct way, pick one weight, the gold line. Change it and rerun the whole network. Watch the boxes light up. The loss ticks up a hair. Divide that change by the change in the weight, the formula on top, and there is the derivative measured. One full run for one weight. With 1,000,000 weights, one step would take 1,000,000 runs, one for each weight. And training takes thousands of steps. This way is a dead end. We need every derivative from a single run, and that is backpropagation. Here is the key idea. One path through the graph is just a chain of small operations from x, step by step, to the loss. Chain them together, and you get a single formula for the loss, the number we minimize. Each link's derivative is easy on its own. The trick is combining them. Take the simplest chain x feeds u, and u feeds y. The first arrow has derivative 2. Push x by 1, and u rises by 2. The second arrow is 3, so each step of u lifts y 3 times as much. Push x by 1, and y moves by 6, 2 times 3. The derivatives multiply. This is the chain rule, the one piece of calculus behind deep learning. There it is. The derivatives multiply along the chain. Any depth, one multiply per link. Now map it onto our chain. Under each link sits its local derivative, and every one is a value the forward pass already computed. The input, the gate, the weight itself, and predicted minus true, free from episode 4. That is why we save the forward values. Backward needs exactly these. Start at the loss end. Differentiating cross-entropy by a score collapses, back in episode 4, to predicted minus true. We call it delta, the error signal, in orange under each score. Now the backward pass begins, and as each saved value gets used, its gold glow turns green. One arrow back, a weight in W2. Its derivative is delta, which we already have, times the hidden value it carried forward. Multiply, and the whole green layer gets its derivatives at once. Now the hidden neurons. This one fed all 3 scores, so its delta is a sum, Each scores delta, weighted by the connection that carried it. Watch the arrows converge. One thing is in the way, ReLU. This neuron landed on the flat side, its output stuck at 0. Push its input, and the loss does not move at all. The local derivative is 0. The gate is shut, and delta stops here. On the ramp side, it passes straight through. The last arrows, W1. Same pattern. Delta times the saved input. Pull back, and every weight now holds its derivative. One photo, one backward walk. The full algorithm. Forward, compute, and save every value in gold. Backward, delta flows left, one multiply per arrow, and each saved value turns green as it is used. That is backpropagation. Here is why one pass is enough. This hidden neuron's delta, the orange chip, feeds the 3 weights leaving it. Instead of recomputing it for each one, we compute it just once, store it, and reuse it. Nothing is ever done twice. Now the bill. One at a time would be 1,000,000 runs, the orange bar. Backpropagation is 1 forward pass plus 1 backward, the green sliver. That gap is what makes deep learning possible. The price is memory. Every derivative is delta times a saved value, so the hidden layer, the gates, even the input all wait in memory until backward has used them. Watch the bar fill. Training eats far more memory than just running the network. Now we use those gradients. Take one step downhill. Every weight shifts a little, the numbers across the net update, and the loss drops. That is a single training step. Then do it again and again, faster and faster. Each pass the values change, and the loss keeps falling until it is nearly 0. Run backward for the gradients. Take a step, repeat. That is how a network learns. Zoom out. Forward, loss, backward, step. That whole thing we just did is one turn of the training loop. It closes and repeats. And it never runs on one photo. Each turn draws a random batch and steps by their average, mini-batch gradient descent. One pass through the whole set is an epoch. Let it run, batch after batch. The loss keeps falling. This exact loop trained every modern network, ChatGPT included. Keep 3 things. Derivatives multiply. The chain rule. Backpropagation sweeps once, reusing saved values, and delivers every derivative. And training is the loop, batch after batch, epoch after epoch. But there is a trap. A deep network multiplies many local derivatives, each a little below one, and the signal shrinks layer by layer until it arrives as almost nothing. Vanishing gradients. Why deep networks refuse to learn. Subscribe to build deep learning from zero with me. And if this made Backprop click, tell me in the comments. Next time on 10 Minute Science.